Okay, so we want to do to see several distinct procedures which allow us to determine if a set of vectors is either linearly dependent or linearly independent. Okay, and there are going to be two different ways to do it. I just want to recall the definitions. So a set of vectors is called linearly dependent if there exist some scalars, not all of which are 0, such that a linear combination of these vectors equals 0. And the reason we said that they're linearly dependent, if this is the case, is because in this case you can move one of them to the other side and express one as a linear combination of the others. So one of them is not necessary, okay, extra. Okay, good, remember that? And they are linearly independent if whenever you have such a linear combination that equals 0, this automatically forces all the alpha i's to be 0. It can only happen when they're all 0. Okay? In other words, this cannot happen. You cannot write one as a linear combination of the others. Okay? And what I want to do now is demonstrate how we determine if a set of vectors is linearly dependent or not by means of examples. So let's start. So here's our first example. We're going to take 3 vectors in R3. V1 is going to be 1, 1, 0. V2 is going to be 1, 0, 1. And V3 is going to be 0, 1, 1. 3 vectors in R3. We want to check if they're linearly independent or not. So, are they linearly independent? So what does it mean for them to be linearly independent? Is there a linear combination, or we can ask, are there alpha i's, in this case alpha 1, alpha 2, and alpha 3, such that alpha 1 times 1, 1, 0 plus alpha 2 times 1, 0, 1 plus alpha 3 times 0, 1, 1 equals 0, 0, 0. That's the 0 vector in R3. If such alphas exist, and they're not all 0, then they're linearly dependent. If the only way to do this is when all the alphas are 0, then they're linearly independent. So let's emphasize, are there alpha i's? Not all 0, some of them can be, such that this holds. And this translates to a system of equations. Like many things in this course translate back and forth to systems of equations. Namely, if this is going to hold, then this translates to alpha 1 times 1 plus alpha 2 times 1 plus alpha 3 times 0 has to be 0, right? So alpha 1 plus alpha 2 has to be, let's leave a space for alpha 3, has to be 0. Do you agree? And in the second entry, alpha 1 plus alpha 3 has to be 0. And in the third entry, alpha 1 times 0, alpha 2 plus alpha 3 has to be 0. So saying that there are, so the question is maybe, let's bullet these. They're all the same question. Does this system of linear equations in the unknowns alpha 1 through alpha 3, does it have, it obviously has a solution where all the alphas are 0, but that would say nothing. Does it have a non-trivial solution? Do you agree? So we translated the question about linear independence of 3 vectors to a question about solving the system of equations. Okay? And we know how to answer this question. We know how to solve the system. We can put the coefficients. This is a very simple example, but we can do it even if the examples are much more complicated. Put the coefficients in the augmented matrix and start doing row operations, etc. Let's do that. Okay, so let's do that. So here's the matrix that we have, 1, 1, 0, 0. It's a homogeneous system, so the B column is actually not very interesting in this case. So let's see. We can do R2, replace it by R3, and we get 1, 1, 0, 0, 0, 1, 1, 0, and 1, 0, 1, 0. Then we can replace R3 by R3 minus R1. Does everybody see exactly the motivation for every step? You're already feeling good with these sort of things, right? Okay, so we get 1, 1, 0, 0, 0, 1, 1, 0, and then R3 minus 1, 1, so we get minus R1, negative 1, 1, 0. Then let's change R3 to R3 plus R2, and we get 1, 1, 0, 0, 0, 1, 1, 0, and 0, 0, 2, 0. And this is already what we called echelon form, right? Do you agree that the first non-zero entry in every row is at least one place to the right from the rows beneath it? Okay, so this is echelon form. And we can already say that the rank of A is the matrix without the B column, okay, in this case equals the rank of A star. A star is the entire augmented matrix, okay, and in this case they're both 3. Do you agree? And 3 was what we called n in this situation, the number of unknowns, okay. So by the theorem that we had, this implies that there is a unique solution to the system. Okay, so the system, the original system of equations, which is on the previous board, has a unique solution. But this is a homogeneous system. A unique solution for a homogeneous system is only the trivial one. The trivial one. Do you agree? Okay. So what was the question we were asking? Is there a non-trivial solution to this system? The answer is no. There's only the trivial solution. Meaning we can now go trace back where we started. This system here only has the trivial solution, meaning that the only alpha i's that solve this are all 0. Meaning that these 3 vectors are linearly independent by definition. Back one board, the only linear combination of the vectors that gives 0 is when all the alpha i's are 0. Good? So let's just sum that up. The conclusion, v1, v2, v3, this set of vectors is linearly independent. Good? By definition. Okay, so let's do another example. I want to do this example. There we go. So, example number 2. We have, again, 3 vectors in R3. V1 is 1, 2, 3. V2 is 1, 0, 6. And V3 is 3, 2, 15. Are they linearly independent? we need to check, right? But let's start doing the logical steps, the equivalent phrasings of the same question, but let's not write everything down. So we want to know if they're linearly independent. So we want to know if there is a non-trivial solution to the linear combination alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 equals 0. Are there alpha i's not all 0 that solve that? Right? That's what we're trying to ask. And that translates into a question about a system of equations. If you put here an alpha 1, okay, then you're going to get, let's translate, so this leads, this is not a canonical symbol in mathematics, this is just my way of saying, let's not do that. So this yields the system which I'm already going to express by in matrix form. Okay, so it's going to be alpha 1 plus alpha 2 plus 3 alpha 3 equals 0. That's going to be the first equation, right? And that's going to be expressed as 1, 1, 3, 0. Do you agree? The next row is going to be alpha 2 times 2 plus, alpha 1 times 2 plus alpha 2 times 0 plus alpha 3 times 2 equals 0. Does everybody understand? I'm pointing at things that are not there. There are no alphas here. But is everybody following? Okay, good? So, and the reason I'm doing this, which is the only reason I'm doing another example, usually one example is enough and then you have to practice on your own, to show you that we don't really need to go through writing everything 3 times. Once you get the idea, you can skip all those intermediate steps. Okay? So the second line is going to be 2, 0, 2, 0. And the third line is going to be 3, 6, 15, 0. And we want to know if this system has a non-trivial solution. If this system has a non-trivial solution, that means that they're dependent. There are alpha i's not all 0, such that the linear combination gives 0. And if the only solution for the system is the trivial solution, then they're linearly independent. Good? So we can start doing row operations on this. And I'm going to put here a ... because I'm not going to specify all the row operations that we do. Let's just write row operations until we reach the echelon form. Okay, so what you recall that the echelon forms are not unique, right? But let's go all the way to the canonical form. So if you go all the way through to the canonical form, you're going to reach this. 0, 1, 2, 0, and 0, 0, 0, 0. This is the canonical form. Okay? And in this situation, what can we say? The rank of A, this matrix, is 2. It's the same as the rank of A star, right? The same as the rank of A star. It's a homogeneous system, okay? But it equals to 2, which is less than 3, which is in, right? So this implies that there is a degree of freedom here, right? There is more than one solution. So there is a non-trivial solution. Good?
Infinitely many.
Infinitely many, true. Once there's a degree of freedom, we're working over an infinite field, infinitely many solutions. So there exists infinitely many solutions to the system, and this implies that V1, V2, V3, this set of vectors, is linearly dependent. We can find alpha 1, alpha 2, and alpha 3 such that the linear combination alpha 1, V1 plus alpha 2, V2 plus alpha 3, V3 gives the 0 vector, and they're not all 0. Good? That's the definition of being linearly dependent. But in fact, we can actually do it. right? Once we reach this stage, we can actually do it. We can find those alpha i's. Okay, how do we find the alpha i's? So we have a degree of freedom. We can choose one of them to be non-zero, right? So let's take, for example, alpha 1 to be 1. Okay, so we don't have a lot of space. Let's try to write it here, and we'll use up this space. For example, choose alpha 1 to be 1, right? If alpha 1 is 1, this equation here, once we're in the canonical form, in the reduced echelon form, it's very easy to solve the system, right? So this says alpha 1 plus alpha 3 equals 0. So alpha 3 is minus alpha 1. So this implies that alpha 3 equals negative 1. Do you agree? Did everybody follow? Right? This says that alpha 1 plus alpha 3 equals 0. And then in turn, this says that alpha 2 plus 2 alpha 3 equals 0. So alpha 2 is minus 2 alpha 3. So alpha 2 is minus 2 times minus 1. So alpha 2 is 2. Okay? So this is a non-trivial solution to the system. Okay? So this implies, so this is a non-trivial solution. We said there are infinitely many of them. Here's one. And now using this, we can actually spell out the linear dependence. Let's do it here. Alpha 1, so 1 times V1, 1, 2, 3, plus alpha 2, 2, plus 2 times 106, plus alpha 3, minus 1 times V3, 3, 2, 15, is gonna equal 0. That's what a solution to the system means. And you can check this. 1 plus 2 minus 3 is 0. 2 plus 0 minus 2 is 0. And 3 plus 12 minus 15 is 0. There you have it. There you have a linear combination of these three vectors, which gives you the 0 vector, but not all coefficients are 0. So for example, you can move, let's say, the third one to the right-hand side, and you get V3 as a linear combination of V1 and V2. V3 is extra. Good? Everybody follow? Is the idea clear? Okay, good. So this is one method of determining whether a collection of vectors is linearly independent or not. Translate to a system of equations. Translate wisely, okay? You don't just write it out as a system of equations. You have to think what you're doing. And notice that in this situation, the vectors, which were column vectors, actually turned out to be the columns of the coefficient matrix of the system. Do you see that? Does everybody see that?
Does it not always be that way?
No, I could give you, for example, row vectors. And they would translate to the same system. They're going to become column vectors. We'll do examples. I can give you polynomials. And you're going to have to extract their coefficients. And you're still going to get a system of equations which evidently doesn't have any x's in it. There are no polynomials written here. Okay, we'll do examples in a minute. Okay? So in this particular case, these were column vectors to start with, not polynomials, not matrices, we started out with column vectors, and they turned out to be column vectors in the matrix that corresponds to the system of equations. Okay? Okay, so this is method one. Translate to a system of equations, determine whether it has a non-trivial solution or not. Everybody good? Let's do method number two. Okay, so method number two for answering the exact same question. Okay, so we're going to need to erase some stuff. Let's erase here. And what I want to do now is, before I show you an example, I want to spell the method out to give you the recipe. Okay, so method one, which we just did, method one, for determining whether a system is linearly, for determining whether a set of vectors is linearly independent or not. Method 1, translate to a system of equations, of linear equations, and determine if there exists a non-trivial solution. Good? That was method 1. Method 2, for answering the same question, is a set of vectors linearly independent? So method number 2 is going to be where's the page I'm looking for? Ah, there it is. Arrange the vectors as rows in a matrix. Take your vectors and spread them out as rows in a matrix. We'll do an example in a second. And then there are going to be two situations. Oh, as rows in a matrix, and do row operations until you reach the echelon form and find an echelon form. Remember that it's not unique. So do row operations until you find the echelon form. If there is a row of zeros in the echelon form, then your original set of vectors, v1 through vk, is linearly dependent. And if not, if in the echelon form there's no row of zeros, then v1 through vk is linearly independent. Okay? Now this may look mysterious. Why is this true? So it, of course, relies on a theorem. Okay? So what I want to do is first do a couple of examples and then take a step back and quote. I'm not going to prove it. It's not a completely trivial theorem, but I'm going to quote the theorem that proves that this method actually works. Okay? But in the example, we're going to see why it works. Okay? We're going to actually see it, but it's just going to be in an example. So let's do an example. So in fact, I'm actually going to use the same vectors from the previous example. Let's use the same vectors from the previous example. So example, v1 was what? 1, 2, 3. v2 was 1, 0, 6. And v3 was 3, 2, 15. Good. So these are our three vectors. Let's do what the recipe tells us to do. Okay? Arrange the vectors as rows in a matrix. There we go. The first one is going to be the first row. The second one is going to be the second row. And the third one is going to be the third row. I arranged the vectors as rows in a matrix. Do you agree? Find an echelon form. We know how to do that. Let's do that. So the first step is going to be, I'm going to take R2 and replace it by R2 minus R1. And I'm going to take R3 and replace it by R3 minus 3R1. So what I get Tell me if I'm right. 1, 2, 3, 0, negative 2, 3, and 0, negative 4, 6. Do you agree? Good? Okay. Next step. I'm going to take R3 and subtract 2 times R2. And I'm going to get 1, 2, 3, 0, negative 2, 3, and 0, 0, 0. Good? That's it. This is echelon form, right? 1, negative 2, 0. There is a row of zeros. Do you see that? Okay, so let's take a different color here. How about blue? Let's take blue. So there's a row of 0 here's, a row of 0 here's, a row of zeros here. Okay, there's a row of zeros here. And that's it. That's all we need to know. Let's go back to the recipe. The recipe said, if there is a row of zeros in the echelon form, your original set of vectors is linearly dependent. That's the situation in that example. It's linearly dependent. If there were no row of zeros, then they were linearly independent. That is not the case in this example. So we can deduce at this point that V1, V2, V3 are linearly dependent. So again, this looks like a mystery. We of course got the same conclusion that we had previously, but why? Why did this work? Okay, you can notice that we did here something completely different. There we put the vectors as, in the previous method, we put the vectors as columns and did row operations. Here we put the vectors as rows and did row operations. This is completely different. We're doing something different. Okay? There we saw exactly what the theory is, where it stemmed from. Where does this stem from? So here's the idea. It's not a proof, it's the idea. Do you agree that this thing here that I'm putting the circle around, what is it? I took R2 and subtracted R1. But R2 was nothing else than V2. And R1 was nothing else than V1. So this really corresponds to V2 minus V1. This is what this row is. Do you agree? Okay? And this row over here, this row, is precisely V3 minus 3V1. This row here is V3 minus 3V1. Do you agree? Now what happened here? This row was what? Was R3 of this matrix, which is not V3. R3 of this matrix is actually V3 minus 3V1. Minus 2 times R2, which was V2 minus V1, gave us the 0 vector. So what this really hides, what's implicit in this procedure that we did, is the following fact. R3 of this matrix, V3 minus 3V1, minus 2 times R2 of this matrix, V2 minus V1, equals 0. That's what everything we did really reveals. Do you see that? And there you have it. This is your linear combination of the 3 vectors that gives 0. Okay, well, V1 appears here twice and they're not in order. Let's fix that. So we have minus 3V1 plus 2V1. So we have minus V1, right? Yeah. And then we have minus 2V2. And then we have plus V3 equals 0. That's a linear combination of the 3 vectors. Not all coefficients are 0. And we got the 0 vector. Do you see that? So this procedure was really just a way of actually setting a linear combination to get 0. And if in the echelon form there was no 0 row, that means that you can't do that. Okay, clear? So, by the way, well, here it's written like this. I can obviously write it as V1 plus 2V2 minus V3 equals 0. That's the same thing, right? And that's precisely the linear combination that we found in the previous example. Okay? We can take a peek here at this board. It's still here. That's precisely this. Do you see that? Okay? But there's a significant difference between the two methods. Okay? And one lesson that you can take out of these two methods is not just that there's a significant difference between the two methods, but moreover, many situations in this course, many things that you're going to do are going to translate to either setting up a system of equations or putting vectors as rows of matrices and doing row operations and so on. But there's always understanding behind it. You can't just take a problem, write the vectors as rows, do row operations, reach the echelon form, and deduce some conclusions. Okay, that's usually false. You have to understand what you're doing and do the right thing. Okay, it's not just everybody understand what means. Okay, so that's this method. Okay, setting up the vectors as rows of a matrix, doing row operations till the echelon form. If there's a row of zeros, then they're linearly dependent. If not, then they're independent. Okay? I want to write the theorem that justifies method number 2. Again, I'm not going to prove it right now. I just want to write it. And after I write it, I want to do some more examples. So here's the theorem first.
Does it matter which vector I put in what row?
It doesn't. It doesn't. Usually when the vectors come with names, v1, v2, v3, we try to stick to those names, but it completely doesn't matter. The property of being linearly dependent or linearly independent is a property of a set of vectors, of a collection of vectors, and there's no meaning to the order between them. Okay? Okay, what do I want to erase? Let's erase this example here and just quote the theorem that we're basing this method on. But I think, at least in this case, it's really more illuminating to understand the example and to see why this holds, why this is true, than just the abstract theorem. But the theorem is important in its own right also. So let A and B be row equivalent matrices. Meaning we can start with A, do row operations, and reach B. Or vice versa. Okay, all these row operations are reversible, right? You can do the opposite operation and go back. So being row equivalent means that you can go from one to the other via row operations. Okay, I'm not saying that one is necessarily in echelon form or canonical form, just any two matrices that you can reach one from the other by row operations. That's what it means to be row equivalent. Okay? Then, the rows of A are linearly dependent if and only if, this is the abbreviation for if and only if, the rows of B as vectors. When you take rows of a matrix, they form vectors, right? As vectors, the rows of one are linearly dependent if and only if the rows of the other are linearly dependent. That's the first theorem. And theorem number 2 says non-zero rows of a matrix in echelon form are linearly independent. Okay? And the third theorem, I think the third theorem I am going to prove. In the next lesson, I want to prove some theorems about sets of linearly dependent and linearly independent vectors. These are more related specifically to matrices. I'm not going to prove 1 and 2. I probably will prove 3. Any set that includes the 0 vector is linearly dependent. So we'll probably prove 3 in the next lesson. But let's see why these 3 theorems yield what we called method number 2. Okay? So what did we do? The first thing that we did was to set the vectors as rows in a matrix. Okay? By setting them as rows, we saw that we're just changing the way we think of them, but we're not changing their entries or changing any other property. Okay? So once we set them as rows in a matrix, if those rows are linearly dependent, then the 3 vectors are linearly dependent. And if they're not, then they're not. Do you agree to that? Okay. So the first theorem tells us we set them as rows in a matrix, call it A, and then we did row operations. Okay? The first theorem tells us these row operations do not change the linear dependence of the rows. Okay, so we moved to a totally different matrix, right? Let's look back at the example. This was our A, the matrix that we started with. We ended up with this matrix, which is obviously a totally different matrix, but they're row equivalent, right? So answering the question of whether these vectors are linearly dependent answers the questions of whether the rows of these matrices are linearly dependent by theorem 1. Okay? Theorem 2 and 3 tell us the following. If there is a 0 vector here, that's theorem 3. If there is a 0 vector here, then the set is linearly dependent, right? That's theorem number 3. Any set that includes the 0 vector is linearly dependent. Do you agree? And theorem number 2 tells you non-zero rows in echelon form are linearly independent. So if the matrix we row reduce to, B, is in echelon form, and it has no 0 vectors, then by theorem number 2, its rows are linearly independent. Clear? So do you see how these 3 theorems, which require proof, general proof, how these 3 theorems yield what we called method 2 and state it as a recipe rather than a bunch of theorems. Clear, everybody? Okay, so what I want to do now is do another example, or maybe a few more examples, of these 2 methods, but I want to apply them not to just column vectors, like we did in all the examples so far, but to various things. Okay? And this is going to relate to things that we're going to study later on in the course of how we can present vectors in alternate ways. Okay? But equivalent. So let me show you what I mean. So I know this lesson is a bit long, but there's a lot in it, and it's important to do many examples to get all the ideas. So that's why it's a bit long. Okay, so here's example number 1. Let's call it example A. I'm going to take V1 to be 1, 2, 3, 4. This is still a column vector. V2 is going to be 2, -1, 1, 0. They look familiar? And V3 is going to be 3, negative 2, 1, 2. And I'm going to ask, are they linearly independent? Okay. We have two methods of doing this. Method number one, write a system of equations. Okay? The system of equations that you're going to get is the following. Alpha 1 V1. So you're going to get alpha 1 plus 2 alpha 2 plus 3 alpha 3 equals 0. Do you see where this came from? Why this is the first equation? I'm writing alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 equals 0, 0, 0, 0. And then spelling out each line separately, each entry separately. This is the first equation that I'm going to get. The second one is going to be 2 alpha 1 minus alpha 2 minus 2 alpha 3 equals 0. The third one is going to be 3 alpha 1 plus alpha 2 plus alpha 3 equals 0. And there are going to be 4 of them here, right? The fourth one is going to, The fourth one is going to be 4 alpha 1, no alpha 2, plus 2 alpha 3 equals 0. Do you agree? Okay. And this is going to, in the next step, we're going to get a matrix, the augmented matrix. We're going to do the row reduction operations, right? And find the answer. Okay? So, so let me write as A star. We know how to do that. Do row operations until you reach the canonical form if you want to go all the way, not necessarily required. And then if there exists a non-trivial solution to this system of equations, then V1, V2, V3 are, or is, the set is linearly, if there exists a non-trivial solution, then the set is linearly dependent. Do you agree? Okay? I'm not going to do all this. You can do it. Okay? Try to do it. Method 2. The reason I'm not doing it is that this is not the point. The point is going to be in examples B and C, and I want to show you how they relate to example A. So B and C, method number 2 is take this and write it as rows of a matrix. Write your vectors as rows of a matrix. So the matrix we're going to get is 1, 2, 3, 4, 2, negative 1, 1, 0, and 3, negative 2, 1, 2. You have to recognize this one, right? If I put a 13, 8, 13 here, would you recognize it then? Okay, so this corresponds to the system of equations that we've been handling in various contexts, and we used this example several times. But now, we're not treating it at all as a system of equations. This is not an A star matrix of some system. Okay? There's no 0, 0, 0 here, and there's no 13, 8, 3 here. It doesn't have anything to do with a system of equations. It's method 2. It's totally different question. Okay? But we know what the row operations on this would yield. Okay? Because we did them several times. So we know this leads, let's do it the same way, row operations. And we know what we're going to get because we did it. So we get 1, 0, 1, 0, 0, 1, 1, 0, and 0, 0, 0, 1. That's the matrix that we get. When this was a system of equations, this implied, I don't know if you remember, that R of A equals R of A star if there was a another column B here if it was, okay? But that's completely not relevant. That's not the question that we're asking right now, okay? We're only asking the following questions. Is there a zero row? That's the only thing we care about. Answer, no. Right? By the method, or by the theorems that we quoted, the rows of this matrix are linearly independent. And by the theorem or the method, the rows of this matrix are linearly independent, and therefore these three vectors are linearly independent. Okay? No zero row. Therefore, V1, V2, V3 are, or is, linearly independent. And you can, of course, verify by answering this question that that is what you would get in method 1 as well. Okay? So is this clear? Is the idea here clear? Okay. So now I want to take this same exact example, but in disguise. So I'm going to write something else that's going to seem taken from a totally different context, but it's going to turn out to be very, very similar. So here's example B. Let's look at three matrices. A1 is going to be the matrix 1, 2, 3, 4. A2 is going to be the matrix 2, negative 1, 1, 0. And A3 is going to be the matrix 3, minus 2, good, 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 1, 2. These are three vectors. These are three vectors in the vector space M2 by 2 over R. Do you agree? So all these three belong to matrices, square matrices, 2 by 2 square matrices over R, which is RV in this case. This is the vector space to which these three vectors belong. Do you agree? And a perfectly legitimate question is, are they linearly independent or not? Okay. Method one, are they linearly independent? Method 1, translate this to a system of equations. Write alpha 1 times this one, plus alpha 2 times this one, plus alpha 3 times this one, equals the zero matrix, 0, 0, 0, 0. That would yield 4 equations, one for each entry. Do you see that? The first one is going to be alpha 1 times 1, plus alpha 2 times 2, plus alpha 3 times 3 equals 0. That's the first equation. The second one is going to be alpha 1 times 2, plus alpha 2 times negative 1, plus alpha 3 times negative 2 equals 0. The third one is going to be, and you keep looking over here, I'm going to move to the previous board and read to you out loud what the third equation is going to be, but you're supposed to be looking over there. 3 alpha 1 plus alpha 2 plus alpha 3 equals 0. Is that correct? Okay. Do you see that we get this exact system of equations? Okay. And once we do that, the answer is obviously going to be the exact same answer. And the reason is that those 4 matrices are in some sense, which we are going to make explicit later on in the course, in some sense, they're the same as these 3 vectors in R4. It's a different vector space, but in some sense they're related. Do you see that? Likewise, we can perform method number 2 on these 3 matrices. Write them as rows of a big matrix. Each row is going to have 4 entries. So you're going to get the first row to be 1, 2, 3, 4. The second row, 2, negative 1, 1, 0. And the third row, 3, negative 2, 1, 2. That's precisely this matrix over here. Do you agree? Okay? And answering this question would be answering the same question. Okay? So although we're working in a different vector space, in a different world, the world of 2 by 2 matrices over R, in fact, we're translating it, there's some mysterious connection between this vector space and R4, in which these 3 vectors really correspond to those 3 vectors. Sorry, these 3 2 by 2 matrices really correspond to those 3 column vectors. Okay? But that's not all. Okay, so I'm not going to write this. Translates, let's just write, translates to example A. Do you agree? Okay? By both methods, you get the exact same thing and the same results. Okay? Let's take this a step further. Let's take, so this is example C. Let's take 3 polynomials. P1 of x is going to be x cubed plus 2x squared plus 3x plus 4. P2 of x is going to be 2x cubed minus x squared plus x. And P3 of x is going to be 3x cubed. Can you tell me what to write?
Minus 2x squared.
Right.
Plus 1x plus 2.
Plus x plus 2. Good. These are 3 polynomials in over R, let's say. So in R3 of x. 3 polynomials of degree less than or equal to 3 over the field R. Do you agree? This is a vector space. This is now RV. Okay? And a perfectly legitimate question is, are they linearly independent? And the way to answer that question would be, well, take alpha 1 times P1 plus alpha 2 times P2 plus alpha 3 times P3. Are there non-zero alphas such that when you add them, when you do the linear combination, you get 0? Do you agree? Everybody with me? Okay, so it's precisely the same question. And this would yield a system of equations, right? If maybe let's write that down. It may be a bit more confusing to see. So alpha 1 times P1, x cubed plus 2x squared plus 3x plus 4, plus alpha 2 times P2, 2x cubed minus x squared plus x, plus alpha 3 times P3, 3x cubed minus 2x squared plus x plus 2. This is a linear combination of polynomials, right? And the question is, can I find, what's this 0?
It's the 0 from the method.
It's the 0 polynomial. The 0 vector in this vector space. Do you agree? And I'm asking, is this linear combination of vectors, the vectors in this vector space happen to be polynomials, is it equal to the 0 vector? The 0 vector in this vector space is the 0 polynomial. Okay, so this is the 0 polynomial. Do you agree? And the question remains the same question. Are there non-zero alpha i's such that I can write this? Or is every time I write a combination like this, if it holds, does it force alpha 3, alpha 2, and alpha 1 to all be zeros? That's the question. Do you agree? Let's do method 1. Let's translate it to a system of equations. Okay? Well, when are 2 polynomials the same? If they have precisely the same coefficients. On the right-hand side, all the coefficients are 0. So if this is going to be an equality of polynomials, all the coefficients here have to be 0. So the coefficient of x cubed is going to be alpha 1 plus 2 alpha 2 plus 3 alpha 3. That has to be 0. And now I'm going to run between the boards. I hope the camera guy can follow me. That's this equation here. Do you see that? The second equation, back to this board, the coefficients of x squared. 2 alpha 1 minus alpha 2 minus 2 alpha 3, those are the coefficients of x squared, they have to be 0. Let's say that again. 2 alpha 1 minus alpha 2 minus 2 alpha 3. There it is. Good? And likewise for x and for the free coefficients. Okay? So it translates exactly to the same system of equations, which is going to have exactly the same solutions. Okay? And likewise, if you would like to set them as rows in a matrix. What does it mean to set them as rows in a matrix? All those x's over there are just to make life harder. Just take the coefficients. 1, 2, 3, and 4 are precisely the coefficients of P1. 1, 2, 3, and 4. They were precisely the entries of this 2 by 2 matrix. 1, 2, 3, and 4. Okay? 2, negative 1, 1, 0 is the same 2, negative 1, 1, 0 when we wrote it as R4. It's the same 2, negative 1, 1, 0 in P2. Do you see that? So again, seemingly totally different vector space is somehow very closely related to this vector space and in turn to R4. They're somehow the exact same vector space in some sense, just disguised differently. Do you see that? And there's a reason for it. Okay, it's not that every two vector spaces are actually the same thing, just looking differently at the same things. It's these three specific ones. R3 of x, M2 by 2 over R, and R4. And there's a reason for it. And, well, all have 4 components is... What do you mean this has 4 components? It's polynomials of degree 3. You're right in some sense, but that's not precise enough. There's going to be a very precise way of saying this fact, but we're not there yet. That's our next main topic, but we're not there yet. Okay, good?
So where to solve this? I would just put...
Well, you wouldn't solve this. You would translate it to that system of equations in method 1 and solve that. Okay? Or you would write the coefficients of these polynomials as rows of a matrix, and you would get exactly that matrix in method 2 over here, this one, and do the row operations and check if there's a 0 row. Good? Okay, so now you know how to handle, using these two methods, things that are not necessarily column vectors. Okay, you can handle polynomials, you can handle matrices, and whenever you see some vector space, there's always going to be some way to extract the data that we really need. So the x's are just blurring the pictures in the polynomials. The x's are not what matters. What matters is the coefficients. Okay? So this is kind of a promo to the next topic, but it's important to see it now. Okay? Okay, so I know this was a pretty long one, but I think we said many things that are very closely related. But cutting this in two in any intermediate point would have been unnatural. But now we're going to stop, and in the next lesson, what we're going to do is go over a few theorems, not hard theorems, that help us to get the feeling for when is a set, in general, not in examples, when is a set linearly dependent, when is it not, if we throw in an extra vector, do we always ruin the linear independence or not, and so on. So that's the next topic.